Hey there, welcome back to the Deep Dive. Today we're going back to a place we all know from our school days, the world of triangles.
Triangles.
You might be thinking, triangles?
Mm.
Really? Didn't we conquer those back in Geometry 101?
Yeah, but trust me, there's way more to triangles than you think. We're going to go beyond those basic rules and dive deep into some fascinating formulas and techniques used to actually solve them.
Okay, so let's unpack that. What does it even mean to solve a triangle? It sounds way more intense than just like finding a missing side or angle or two.
It's kind of like the difference between knowing the layout of a house and actually understanding its intricate wiring and plumbing. Solving a triangle means we uncover all its hidden relationships, not just sides and angles, but also its area, the circles we can draw inside and around it, special points of intersection, and so much more.
I like that analogy. It sounds like we're going to be uncovering a whole hidden world within these seemingly simple shapes. So where do we even begin with this deep dive?
Let's start with the basics. We know a triangle has three sides and three angles.
Right.
Mathematicians use a standard notation. A, B, and C for the angles, and lowercase a, b, and c for the sides opposite those angles.
Right. So capital letters for angles, lowercase for sides. It's like a secret code for unlocking the mysteries of triangles. What else should we keep in mind as we go deeper?
Two key concepts will come up a lot.
Okay.
Circumradius, denoted by R,
Okay.
and area, represented by D.
I'm picturing the circumradius as the radius of a circle that like perfectly hugs all three corners of the triangle.
Yeah.
Kind of like a custom-fit halo, am I right?
Exactly. It's like finding the perfect circular frame for our triangle.
Right.
And the area, well, that's familiar. The amount of space enclosed within those three sides. Now, let's talk about the tools that help us unravel these secrets. First up, the sine formula.
Okay.
It's more than just a formula. It's like a statement about a fundamental relationship in any triangle.
I remember the name from high school, but honestly, the details are a bit fuzzy.
Yeah.
Something about ratios, right?
Right. The sine formula tells us that the ratio of a side of a triangle to the sine of its opposite angle is constant. It's beautifully represented as a sin A equals B sin B equals C sin C equals 2R.
Wait, so this means if I pick any side and its opposite angle, that ratio will be the same as any other side and its opposite angle in the same triangle. And it's equal to twice the circumradius, too. That's kind of mind-blowing.
Exactly. It's like a hidden code embedded within every triangle.
Yeah.
And here's the cool part. This works for any triangle, not just right-angled ones.
So we have this powerful tool, the sine formula,
Right.
that helps us connect sides, angles, and even the circumcircle. Can we see it in action?
Absolutely. Imagine a triangle where the angles are in a specific ratio, like 4.1.1. By applying the sine formula, we can actually figure out the ratio between the longest side and the perimeter of the triangle. It's like solving a geometric puzzle.
That's incredible. It's like the sine formula gives us this key to unlock hidden proportions within the triangle. I'm already starting to see how much more there is to these shapes than I ever realized.
And we're just getting started. Let's move on to another powerful tool in our triangle toolkit, the cosine formula.
The cosine formula. That takes me back to trigonometry class. But before we get lost in the formula itself, can you give us a sense of what it's actually doing? How does it connect sides and angles in a way that's useful to us?
Great question. The cosine formula provides a direct link between the lengths of the sides of a triangle and the cosine of one of its angles. Let's look at the formula. AUBH equals B plus CPF 2BC cos A.
Okay, I see the familiar Pythagorean theorem lurking in there.
You're right, it's closely related. If angle A is 90 degrees, the cosine term becomes 0, and we're left with the Pythagorean theorem.
Right.
But the beauty of the cosine formula is that it works for any angle, not just right angles.
So with this formula, we can solve for a missing side if we know two sides and the angle between them. It's like a magic measuring tape for triangles.
Precisely. And it doesn't stop there. We can rearrange the formula to solve for the cosine of an angle. Imagine you know all three sides of a triangle. You can use the cosine formula to find any of the angles.
That's amazing. It's like having a decoder ring for triangles, figuring out angles just from the lengths of the sides. Are there other formulas out there, each with its own special purpose in the world of triangles?
There are indeed. For instance, the projection formulas. They might not be as famous as the sine and cosine formulas, but they're surprisingly useful. They connect a side of a triangle to the projections of the other two sides onto it.
Projections. So we're talking about shadows of the sides, like how a movie projector casts an image on a screen.
It's a similar concept. Imagine shining a light directly above the triangle. The projection formula helps us relate the length of a side to the shadow that the other two sides cast onto it. What's fascinating is these formulas can sometimes simplify geometric proofs, making them more elegant and easier to understand.
Wow, I'm starting to see the depth and complexity hidden within these seemingly simple shapes. What other triangle treasures are waiting to be discovered?
Let's talk about Napier's analogy, sometimes called the tangent rule. Now, this one sounds a bit more complex, but it provides us with a really neat relationship between the tangents of half the sum and difference of two angles in a triangle.
Okay, tangents. Things are getting a bit more technical, but I'm still with you. So this Napier's analogy helps us connect half angles and tangents within a triangle. I'm curious to see how that plays out.
What's interesting here is that Napier's analogy often comes in handy when we have information about the tangent of half the difference of two angles and need to figure out the ratio of the sides. It's a very specific tool, but a powerful one when we need it.
So it's like a specialized decoder ring for specific triangle problems. I'm loving these analogies. It definitely helps to make these concepts more approachable.
Good.
What else is in our triangle toolbox?
Next up are the half-angle formulas. They're especially useful when we know the lengths of all three sides and want to figure out the angles.
These formulas involve a concept called the semi-perimeter, which is simply half the perimeter of the triangle.
Semi-perimeter, okay, that's easy enough to remember, half the perimeter. So if we know all three sides, we can find the semi-perimeter and then use these half-angle formulas to crack the code of the angles.
You got it. It's like working backwards from the sides to discover the angles. And these half-angle formulas lead us to another intriguing formula, the formula for the area of a triangle.
Wait, so we can find the area of a triangle just by knowing its sides. No need to draw altitudes or anything.
Exactly. The formula is D, SA, SB, SC, whereas S is that semi-perimeter we just talked about. It directly connects the sides of a triangle to its area, which is pretty neat, don't you think?
Totally. It's amazing how these formulas provide shortcuts and reveal hidden connections within triangles. And I'm guessing there are even more specialized formulas out there for specific situations, right?
Absolutely. There's the MN theorem, for instance. This one comes in handy when we have a line that divides the base of a triangle into two segments of lengths, MNN. Okay, let me visualize this. So we're basically slicing the base of the triangle, and this theorem helps us understand what happens next.
Exactly. The MN theorem gives us a relationship between those lengths, M and N, the angles formed by that dividing line, and the other angles of the triangle. It's like adding another layer of complexity, but also another layer of understanding.
Wow. It's incredible how these formulas seem to unlock all sorts of hidden connections within a triangle. It's like they reveal a secret language that governs these shapes.
I like that analogy. And speaking of hidden connections, let's delve into the world of special points in a triangle.
Okay?
The incenter, the circumcenter, excenters, and the orthocenter. Each of these points plays a unique role in the geometry of the triangle.
Okay. Those names are ringing a bell from somewhere deep in my memory, but I definitely need a refresher. Can we break those down one by one?
Of course. Let's start with the incenter. Imagine drawing lines that bisect each angle of the triangle.
Okay.
The point where those three angle bisectors meet. That's the incenter.
Right, so it's like the heart of the triangle where all the angles come together. And why is it called the incenter?
Because it's also the center of the circle that fits perfectly inside the triangle, touching all three sides. This circle's called the incircle, and its radius is called the inradius, denoted by R.
So the incenter and inradius tell us about the circle that lives happily within the triangle. What about the circumcenter?
Remember that circumcircle we talked about earlier? The one that passes through all three vertices of the triangle?
Yeah.
Well, the circumcenter is the center of that circle. It's the point where the perpendicular bisectors of the sides of the triangle all meet.
Okay, so the circumcenter sits above the triangle, like a crown, marking the center of that all-encompassing circle.
Yeah.
What are those excenters? They found a little mysterious.
Think of them as the secumcenter's extended family. Each triangle has three excenters, and each one is the center of a circle that's tangent to one side of the triangle and the extensions of the other two sides. It's like having a family of circles associated with each triangle.
So we have the incircle tucked inside the triangle, the circumcircle encompassing it, and then these excircles dancing around the outside. What about that last point, the orthocenter? Where does it fit into this triangle family portrait?
The orthocenter is where all the heights of the triangle converge. Imagine drawing a line from each vertex straight down to the opposite side, making a 90-degree angle. Those lines are called altitudes, and the point where they all intersect is the orthocenter.
Got it. So we have these four special points within a triangle, each with its own geometric significance. And I'm guessing they don't just exist randomly, right? There must be some fascinating relationships between them.
You're absolutely right. These special points aren't isolated entities. They have amazing relationships with each other.
Hmm.
For example, the centroid, which is the point where the medians of the triangle meet, divides the line segment joining the orthocenter and circumcenter in a very specific ratio.
Wait, the centroid, orthocenter, and circumcenter are always connected in a specific way. That sounds intriguing. What's the ratio?
The centroid divides the line segment joining the orthocenter and circumcenter in the ratio of 2.1. It's like a hidden blueprint governing the arrangement of these points, a testament to the elegant order within triangles.
This is incredible. It's like uncovering a secret society within the world of triangles with these special points connected in ways I never imagined.
That's exactly the spirit of solving triangles. It's about going beyond the surface and revealing the deeper connections and relationships that make these shapes so fascinating. Now that we've got our toolbox filled with formulas and a better understanding of these special points, we're ready for the main event, actually solving triangles.
Finally, this is where we put all our knowledge to the test and start cracking the codes of these shapes. I'm ready for the challenge.
Then let's dive into the different cases of triangle solutions, depending on what information we're given. Get ready for some aha moments as we piece together the clues and reveal the full picture of each triangle. Let's start with a scenario where we know all three sides of a triangle, but none of the angles. This is called the SSS case. Side, side, side.
Okay, SSS. Got it. But if we only know the sides, how do we even begin to figure out the angles? It feels like we're missing a crucial piece of the puzzle.
That's where our cosine formula comes in handy. Remember how it connects sides and angles? We can actually rearrange the formula to solve for the cosine of an angle. Then, using the inverse cosine function, we can find the angle itself.
So we're using the cosine formula like a reverse engineering tool. Plug in the side lengths, do some calculations, and boom, we've got the angle. That's pretty clever.
It is.
What about other scenarios? Let's say we know two sides of a triangle and the angle between them. What's that called?
That's the SAS case. Side, angle, side. Again, the cosine formula is our friend here. We can use it to find the missing side. Once we have that, we can use either the sine formula or the cosine formula again to find the remaining angles.
I'm seeing how these formulas are like keys that unlock different aspects of the triangle depending on what information we have. It's like having a detective's toolkit for solving triangle mysteries.
I like that.
But what if we know two sides and an angle that's not between them?
You've just stumbled upon what's often called the ambiguous case, also known as SSA, side-side angle. And it's called ambiguous for a reason. It's possible to have two different triangles that fit the given information.
Wait, two different triangles from the same clues? How is that even possible? That definitely throws a wrench into our detective work.
Let's visualize it. Say, sides B and C and angle B.
Yeah.
If side B is shorter than side C multiplied by the sine of angle B, you can't even form a triangle.
Right, that makes sense. Side B needs to be long enough to actually reach the other side and create a closed shape. Too short, it won't connect.
Exactly. Now, if side B is exactly equal to side C multiplied by the sine of angle B, something interesting happens. You get a right triangle.
So the side perfectly aligns to create a right angle, a special case within the ambiguous case.
Yeah.
What happens if side B is longer than side C multiplied by the sine of angle B?
Now, things get really interesting. If B is longer than that product, but still shorter than side C itself, we can form two different triangles. One will have an acute angle C, and the other will have an obtuse angle C. It's like the side can swing in two different directions, creating two different triangular shapes.
So it's like a choose-your-own-adventure triangle. But what if side B is longer than both the product and side C?
In that case, only one triangle is possible, and it will have an acute angle C. So the relationship between the sides and the angle determines how many valid triangle solutions we can get.
The SSA case definitely lives up to its name. Ambiguous indeed. It's like a triangle puzzle with multiple possible solutions. What about when we know one side and two angles? Is that also a tricky case?
That's the ASA case, angle, side, angle. And actually, it's pretty straightforward. Since we know the angles of a triangle always add up to 180 degrees, we can easily find the third angle. Then we can use the sine formula to find the missing sides.
So we use the angle sum property to get all three angles, and then the trusty sine formula takes care of the sides. Makes sense. What about when we know two angles and a side that's not between them?
That's the AAS case, angle, angle, side. It's very similar to ASA. We find the third angle using the angle sum property and then apply the sine formula to calculate the missing sides.
Okay, so ASA and ASS are kind of like twins,
Hmm.
both fairly straightforward once we remember that angle sum property.
What if we only know the three angles, though? Can we solve the triangle then?
Great question. If we only know the angles, we can't actually determine the sides uniquely. We can have infinitely many similar triangles that have the same angles, but different side lengths.
Right, it's like having scaled up or scaled down versions of the same triangle. So in that case, we can only figure out the ratios of the sides using the sine formula, not the actual lengths.
Exactly. The sine formula gives us the proportions, but not the actual scale of the triangle. It's like knowing the shape of a building, but not its actual height. This is all starting to click. We've gone through all these different triangle scenarios, and I feel like I could actually solve a real triangle mystery now.
And that's just the beginning. We can apply these triangle concepts to even more complex situations. For instance, we can use these principles to analyze regular polygons, shapes with equal sides and equal angles.
Whoa, regular polygons. That brings back memories of those geometric shapes.
Yeah.
Squares, pentagons, hexagons, and so on. But how do triangles fit into that picture?
Think about it. You can break down any regular polygon into a set of congruent triangles. And with our newfound triangle knowledge, we can use trigonometric formulas to calculate the perimeter and area of any regular polygon.
That's incredible. So even though they're not triangles themselves, we can use our triangle expertise to understand them. It's like having a master key that unlocks a whole world of geometric shapes.
Exactly. And that's what makes triangles so fundamental to geometry. They're the building blocks, the foundation upon which we can explore more complex shapes and concepts.
This deep dive has been truly eye-opening. I'm seeing triangles everywhere now, and I'm starting to appreciate the incredible depth and complexity hidden within these seemingly simple shapes. But before we move on, I have to ask, are there any really surprising or counterintuitive things about triangles that we haven't covered yet? Something that would truly blow my mind.
There are always more fascinating facts to uncover when it comes to triangles.
I can only imagine. So what's one of those unexpected truths about triangles that might make our listeners rethink everything they thought they knew?
Here's one that might surprise you. Did you know that in any right triangle, the sum of the squares of the sides is equal to 8 times the square of the circumradius?
Whoa, hold on a second. That sounds like a mouthful. Can we unpack that a little? What does that actually mean in simpler terms?
Imagine our right triangle again, with that circumcircle perfectly framing it, passing through all 3 vertices. This relationship tells us there's a direct connection between the lengths of the sides of that right triangle and the size of that circle, specifically its radius, the circumradius.
So the size of the circle is tied to the lengths of the sides in this very specific way.
That's pretty wild. It seems like there's always a new layer to uncover when exploring triangles.
Exactly, and that's what makes geometry so endlessly fascinating. There are hidden connections and elegant relationships woven throughout these shapes, just waiting to be discovered.
I'm definitely feeling inspired to go out and explore more triangle geometry. But before we wrap up this deep dive, I think it's time for a challenge for our listeners.
I love a good challenge. What do you have in mind?
Let's give our listeners something to ponder, something that will spark their own triangle investigations out in the real world. So here's a final thought for you, dear listener. Think about how you could apply these triangle concepts to everyday situations. Can you see triangles differently now?
That's a great challenge. Encourage them to look around with a geometric eye. They could estimate the height of a tree using the sine formula, or figure out the distance across a lake with the cosine formula. It's like giving them a set of triangle-powered superpowers. Exactly. And who knows what amazing discoveries they might make. So to all our listeners out there, go forth and become triangle detectives in your own world. Share your findings with us. We'd love to hear about your adventures. Thanks for joining us on The Deep Dive.
Until next time, keep those triangle brains buzzing.